Hello, everyone, and welcome to the openEuler Meetup. Today, it's a meetup for container runtime. We'll discuss the future of Sandbox. I'm your host, Jing Xiaolu. Today, we are excited to have 5 distinguished speakers, and they will share their expertise and informative insights on those 4 innovative open source projects with us. Here's our today's list. The first topic is WebAssembly as a container runtime. It's from Dr. Michael Yuan. He is the creator, maintainer of Blossom Edge, and co-founder of Second State. Welcome. And following that is Quark, High Performance App Kernel Sandbox. It's from Dr. Yulin Sun, CEO of QuarkSoft and maintainer of the Quark Sandbox project. Next, Quasar, an efficient multi-sandbox container runtime, is from Sabafeng. He is a container infrastructure expert and currently the maintainer of Quasar. After that, Tao Zhong, an Islamic contributor and openEuler container engine expert, will present her topic on Islamic, a lightweight container engine. Last but not least, Xuepeng Xu, an open source ethicist and a contributor to both Islami and Quasar, will share us his experience on Islami and Quasar, reshaping the container runtime. So now, let's turn it over to our first speaker, Dr. Michael Yuan. Okay, thank you.
All right. Hello. Hi. Thank you, Xiaolu. Let me share my screen. All right. So can everybody see that?
Yep.
Okay. All right. Thank you. Yeah. So hello. It's a pleasure to be the first speaker to to present in this meetup. Sorry for my background. I'm in a hotel in Tokyo, so it's rather cramped. So yeah. So the topic I want to talk about is WebAssembly as a container runtime. I think it's highly relevant to openEuler and also to Quasar because as we'll discuss in a minute, one of the goals is to bring a variety of different container formats into the cloud native ecosystem, right? So WebAssembly is being one of the first technologies that are being supported on those technology stacks. So yes, start. So perhaps I think I have 20 minutes also. So so I'll start with a very brief introduction of what WebAssembly is. It's sometimes it's hard to explain what WebAssembly is and how it's related to containers because the name is very misleading. It's not web and not assembly, right? So it's however, when it was started, it was about running C++ compiled applications on the web. Meaning that you want to run, so the idea, this problem has always existed. That's on the web we have HTML, CSS, and JavaScript. Those are all fairly slow technologies, but people want to play games in the browser. So they want to compile C++ applications or Rust or Go applications and have them run in the browser. However, the challenge for that really is that the browser cannot run native code because it has all kinds of security issues because those code are just downloaded from the internet. If you just let them run in the browser, it's gonna cause harm to the user because it crashes the browser or steal data, whatever. So what they do is that I think starting from almost 25 years ago when Java first came along, it was the same idea is that I have some kind of virtual machine in the browser that runs assembly language code. So C++ or other language or Java for that matter can be compiled into a bytecode format that is look like assembly language. and then you can have high performance applications running in a sandbox inside the browser. So that's the whole idea. That's how this thing gets started, right? So WebAssembly actually started in 2010. When Alan Zakai, when he's at Google now, at the time I think he's at Mozilla, and so he started experimenting with high performance JavaScript. And then fast forward to 2019, right before the pandemic, WebAssembly becomes the fourth language for the web, meaning it's the fourth official recognized standard in W3C. So W3C recognizes HTML, CSS, JavaScript, and WebAssembly, right? So it has gone through the whole process of providing a secure and high performance sandbox for the browser. Okay, but one interesting thing about it is if you provide a sandbox or isolation format for the browser, you can use it on the server too, right? Because that's essentially how Java on the server gets started. That's also how JavaScript on the server, Node.js got started. Is that you have a technology that can reliably and securely run in the browser. And the browser is a very hostile and a very unpredictable environment. You will be able to run the same technology on the server as well and have all the benefits of what we today know as container runtime, essentially security and isolation sandbox, right? So as you can see, from 2019, right before the pandemic, around the time WebAssembly was standardized about W3C in the browser, it has become, people are working on providing systems what we call WASI system interface. If you think about WebAssembly in the browser, it's mostly interact with JavaScript, so it doesn't need to know the things like file system or networking or underlying CPU and GPU, things like that, because JavaScript provide all those functionalities to the WebAssembly runtime. However, if you want to run it on the server, it has to run directly on top of the operating system. So it needs things like networking access, file system, environmental variables, and things like that. So that's what WASI has been born. WASI essentially is a POSIX standard for WebAssembly so that it can interface with the operating system underneath it. And once you have that, it lays the foundation of running WebAssembly really as a container, as being managed by Kubernetes at the same level as, say, Linux container, Docker container, and things like that. So fast forward, we went through the whole pandemic. I, there's lots of discussions and conferences, and then by the end of 2022, CNCF Cloud Native Computing Foundation has released a survey that has a very strong statement. It said containers are the new normal. Container has become the normal. WebAssembly is the future. Is that meaning on the adoption curve, the container has reached the mainstream stage, and WebAssembly is reaching the early adopter stage. So if we look at this survey, which I find it's very interesting, because it's the official annual survey, it's the official survey CNCF does for, I think CNCF has over 1,000 member companies that are paying at least $5,000 a year, and a couple hundreds projects that are different stage of sandboxing and incubation. And so it covers a large swath of cloud computing users and developers. And this whole annual survey of CNCF has only one key findings. It doesn't have multiple key findings. There's only one. Containers is normal and WebAssembly is future. Is find that 37% of the users are already using WebAssembly in the cloud native environment. I don't think it's necessarily using it as a container at the moment. A lot of those use cases are using it as a extension mechanism. But we're going to focus on the container use case for the rest of this talk. And you can see, some of the popular WebAssembly runtimes. Wasm has become the most popular one on the server side. I think primarily because this is the CNCF survey, and Wasm is a CNCF project. So, like many technology before that, especially Java and JavaScript, WebAssembly get massive success in the browser and become the standard. And then it become obvious. The same characteristics that has made it successful in the browser can also make it successful on the server. So when we talk about WebAssembly on the server or WebAssembly as a container, we have to go back to 2018, end of 2018, when Solomon Hykes is I think, it's a well-known person. It's a founder of Docker. It's the original CTO of Docker, right? He tweeted at the time, if WASM, WebAssembly plus WASI, WebAssembly system interface, what I just talked about, the POSIX interface for WebAssembly, existed in 2008, we wouldn't have needed to create Docker. Docker would not have existed, okay? That's how important it is. WebAssembly on the server is the future of computing. he said that almost 4 years ago, right? That's so as you can imagine, when he said that, there's an uproar in the community. There's lots of people who's very invested in, say, Docker and Linux container. They will come out and say, is it really true? That's Linux container would not be important in the future anymore. So most people missed the tweet that he had follow up. So he said, well, what Wasm replace Docker? No. But imagine a future where Docker runs Linux containers, Windows containers, and Wasm containers side by side. Over the time, Wasm might become the most popular container type. So what he visions is a container runtime that runs different type of containers, which is exactly what Quasar is, right? So I think a couple of years later, fast forward to 2023, the ecosystem has finally matured to a point where where we need Linux container, but we also need other types of containers. Wasm container being one of them, perhaps even the most important one of them. So this is, I think a very interesting prediction that the founder of Docker himself has made over 5 years ago, right? So that's a little detour. So well, this is Wasm Edge runtime is one of the WebAssembly runtimes out there, and this is our project. This is also one of the projects that's integrated with Quasar. So it's we position it as a cloud native WebAssembly runtime, meaning that a lot of the WebAssembly runtimes in the past has its roots in the browser. So they are focused on interaction with JavaScript and the browser environment. And Wasm Edge started in 2019 from the get-go. It was to support WASI. It will support running directly on top of operating system. We are not integrated in the browser, in the browser in any way. Although now we are integrated into browser because there's no new generation of browsers are looking for lightweight and high performance WebAssembly runtimes. Some of them use Wasm Edge, but the design principle of Wasm Edge is really to do a cloud native WebAssembly runtime. So we're talking about WebAssembly may be the next container format. It may replace Docker. It may not. That may supplement Docker. But why? It's what is the problem it's trying to solve, right? That's people are using a Linux container as an isolation format, or virtual machine as an isolation format for a very long time. What are the problems that has recently emerged or has always been there that that requires WebAssembly to solve, right? So I think it boils down to mostly performance and footprint and security, right? So compared with a Linux container image, WebAssembly image that does similar things. We are talking about things like AI inference. So a lot of people use Wasm Edge to do AI inference, image recognition, and things like that. If you do that in a Linux container with Python and with PyTorch and with the whole stack of things, the container image could easily be 1 GB, 2 GB. We have all seen that. That's which makes it really hard to run it on the edge, on the home router, on the camera, things like that. But with Wasm Edge plus PyTorch, Wasm Edge plus TensorFlow, you can get the whole image size down to like 40 megabytes, and or even less, right? So it's essentially, that's so for most smaller models, that's that's a very compelling story to have something that is much smaller. Okay. And it's much faster startup time. That's there's many different benchmarks, but some of the benchmarks that show, it depends on what you are comparing to. If you are comparing to, say, AWS Lambda with a Java runtime, that startup time could be in the seconds. It's 5 seconds, 6 seconds. That's easy, right? That's but WebAssembly startup is typically in milliseconds, under 10 milliseconds. So you could see, say, 1,000 times faster performance improvements. At runtime, it also has a large amount of performance improvements over, say, something like Python or or JavaScript, right? And it's secure by default, and meaning that's by default it doesn't have access to any of the operating system features. You have to specifically declare what operating system features that you want to give it access to, and because it doesn't have an operating system inside the runtime, so it has a very small attack surface. It's impossible to say, I forgot to turn off the web server inside the container image because there's no web server in the container image. There's no Apache or Nginx in there. It's just a WebAssembly runtime. So it's a very small attack surface. And it's completely portable. Unlike Linux container, the container image depends on the underlying CPU architecture or even GPU architecture. Say if I tell you, do a Docker image for NVIDIA GPU, that's a major effort. Take multiple days. But for WebAssembly, it's because it runs in the browser, so it abstracts away all the underlying hardware features, and so you can have access to GPU, you can have access to different type of CPUs, RISC-V. You can also, and it's also operating system agnostic. We have made it running on OpenHarmony and real-time operating system as well. So there's lots of things that we made it, it can become a platform independent runtime, and it plays well with um, 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 uh, service orchestration framework. That's where Quasar comes into play, right? Which we're going to talk about in a minute. So we have published papers on IEEE about the performance characteristics of WebAssembly, but this is a performance study that's recently, I think it's last week, done by ARM. So developers uh, at ARM has compared WebAssembly with, I would say, a naked container, meaning that the container doesn't contain any operating system. So basically, they have a simple application that compiles WebAssembly. The application itself is written in Rust. It can compile to WebAssembly and it compile into a native format for ARM. And then ARM runs it in a Scratch container, so it doesn't have an operating system in the container, which is the fastest way possible to run the container, right? So if you look at the startup with the size, the boot up time and the runtime memory use, and WebAssembly is a clear winner, even with the most slimmed down and the most because if you don't have operating system in the container become utterly unportable. It heavily depends on what libraries the underlying operating system going to provide, right? So WebAssembly retains its feature of security and portability, but still wins at performance, right? So this is I find it's interesting because it's done by a completely impartial third party, which is ARM, right? So there's another way to look at it. The benefit of WebAssembly. Those are the two tweets that we send out that has generated some interest community feedback. And by the way, the WasmEdge Twitter account is not a huge account. It's only like 1,000 followers, but you can see both of those tweets have over 10,000 views. Meaning that there are a lot of people on Twitter shared them and it were widely seen. So the first one is that we demonstrated a complete Redis application, a Redis client that runs in WebAssembly inside, the Docker desktop. The entire application size is 700 kilobytes. Okay, so we are talking about a complete microservice or a cloud native type of application that is measured in kilobytes. If we are doing this, say, we even have a slim Ubuntu container plus the Redis library, plus the whatever the language frameworks that is required to run Redis library, like say a Python Redis library or JavaScript Redis library, you can easily run into tens of megabytes or even hundreds of megabytes, right? So people find this very surprising. That's you can have a completely functional application that has a clear comparison to a Linux container application for such a small size, right? So on the right side, it's a very similar tweet, but instead of doing Redis, we're doing PostgreSQL, right? So with PostgreSQL, the application that does the create, read, update, and delete is only 800 kilobytes, 0.8 megabytes. So instead, if you look at the official Docker distribution of, say, application that has a Postgres driver in it, right? That's you are looking at again tens of megabytes in here. So the resource saving and space saving is very significant when you use WebAssembly as a runtime, as opposed to a traditional container runtime, a Linux runtime. So, but just to have the runtime is not enough, because the cloud native ecosystem has evolved in such a way that a lot of those depends on orchestration and the container management. So the container runtime has to work well with all the container management tools. And at WasmEdge, we invested in a lot of time to do that. So on the panel at left is the work that we have done with Red Hat. So WasmEdge is now official package in Red Hat Enterprise Linux. So we are in Real 8 and Real 8 and Real 9. And so it's part of the OpenShift ecosystem. And what that does is that at the OCI content runtime level, at C-run level, and so in OpenShift, they can support CRUN and Yuki. So both CRUN and Yuki are configured to support Wasm Edge, meaning that when they see a container image, it would automatically decide whether it's a WebAssembly image or it's a regular Linux container image. If it's a WebAssembly image, it starts Wasm Edge to run it, right? So it does a bifurcation, when it sees the container image, right, at the CRUN level. And then the work we did with Microsoft is to integrate as container D level. So it's another container D shim called runwazi. And that's work we worked with Microsoft Azure and Docker Desktop. They go this route. So instead of go all the way to the OCI runtime and replace CRUN, they are making the judgment of whether this is a Linux container or it's a WebAssembly container at the container D level. So at the container D, they can go to execute, use WASM to execute the WebAssembly image, and then use the runc to execute the Linux container image. So both are good. It just happens at different level of abstraction in the Kubernetes stack, right? So that leads us to Quasar. That's with Quasar we have now Quasar, we have now perhaps more interesting approach. This approach is similar to the container D run WASI approach that we described, right? That's essentially the Microsoft and Docker approach. And however, it's not just the container D shim. It's leverage more of the container D APIs like the Sandbox API and things like that. So it's provide a tighter integration. So we really look forward to make Wasm Edge the first class citizen in the Quasar container D ecosystem. So let me see. Yeah. So I don't think I have a lot of time, but I do want to touch upon um, some limitations, because I think that's also important, because if you look at Solomon Hayek's first tweet, he basically said, it's possible WebAssembly going to replace Linux containers, because he said we wouldn't have done Docker, if this thing existed, right? But then he wrote it back to say, oh, maybe it's a coexisting ecosystem. And that's actually we believe in the second statement. So although we are WASM, runtime company, we believe WASM would not replace containers because the reason is also very simple. Is that because it doesn't really provide a general operating system environment. It doesn't fulfill Docker's or Linux containers promise of what runs on my computer going to run on your computer as well, because I can just ship the Docker container, with my application, right? In WebAssembly, because it's a new bytecode format, it doesn't have an operating system there. That's why it is fast, it is secure, and it's lightweight. And in order to have all those features, it needs its own byte format, which also means you have to recompile your application. Sometimes you need to rewrite your applications for this particular use case. So WebAssembly is more suited for, say, new applications or applications that really require performance, or applications that needs to be run on the edge. That's also where the name Wasm Edge come from, right? It's that there's places where, say, Linux container is too big or difficult to fit. That's why we need, I think those are the sweet spots of, WebAssembly applications. That's so what are those? One of course is microservices, right? Today, most microservices are written in languages like Go or Java, some are Rust, and they were all packaged in Linux containers. Multiple services can exist in the same pod, managed by Kubernetes, things like that. So, but there's lots of microservices use cases where, say, log processing, and as microservices become more and more finely grained, it's this pattern has become more and more heavy, right? Say, let's use the example. It's common microservice is to process logs. Traditionally you have the ELK framework, right? Elasticsearch, Logstash, and okay, that's those are three JVMs, and three JVM packaged in its Docker Linux container, which contains its own operating system. And to do what? Just to do log processing, right? With Wasm Edge, you can have one container that has that's a simple application written in Rust and wrapped around in a Wasm Edge container and runs in the same Kubernetes cluster as the entire ERK stack, which takes like 1% of the size and has much higher throughput, to process, say, MySQL bin logs. Forward MySQL logs to Kafka, forward MySQL logs to Red Panda, use cases like that. And then streaming data functions, meaning that's I think more and more so the data processing frameworks like YOMO, EMQ, Kafka, Red Panda, those are all our integration partners. They want to build their own processing into their messaging frameworks. However, the processing functions are provided by third party developers. So you would need to provide isolation for them, right? So that's another good use case of WebAssembly. So serverless functions for SaaS is another one. As SaaS become more and more complex, a lot of times people instead of interacting with SaaS using API from outside, people needs to embed third-party code directly into SaaS. One of the great examples that has shown is ChatGPT, right? ChatGPT has an API, OpenAI has an API, but does a lot of people use that API? Some people do. But by far the most popular use case is plugin. Is I write some application and put the code into and have some of them, a part of my code runs inside the ChatGPT platform. In order for that to happen, I need some kind of isolation, need some kind of container, container runtime, and in this case as well, a lightweight, container or lightweight isolation sandbox would be able to play a major role here. So yeah, I think that's my 20 minutes, and thank you so much. And um, um, as I mentioned, Quasar is really the orchestration and runtime framework that the industry has been looking for quite some time. That allows us to mix and match different workloads in their own optimized container runtimes. And I really look forward to collaborating further in the open source community with Quasar and openEuler. Thank you.
Okay, thank you, Michael. It's very, very exciting presentation. Okay, thank you. It's happy to see you again in openEuler. Yeah, it's been 2 years. Yeah, but 2 years ago is the first time you share your resume to openEuler in our Cloud Native second meeting. Yeah, could you please update us some key achievements on resume for the last 2 years? Okay.
Yeah, so I think one of the big things about Wasm Edge is it's now integrated into many more places, right? So we're now in Docker Desktop. So people say, "Oh, I don't know if I have Wasm Edge installed on my computer." I say, "You are developing cloud native application. In high likelihood, you already have, because we are bundled with Docker Desktop." So if you have Docker, you probably do. That's allows to use the entire Docker tooling, including Docker Compose and things like that, to manage Wasm Edge containers side by side with Docker with Linux containers. So we have several examples where we have we have a three-tier microservices. There's a web server, there's one which acts as a proxy. There's a database server, which is a MySQL, something like that. Then the business logic sits in the middle. So the business logic used to be in a container written in Java, application written in Java or Python, but put in the Linux container. But now we can replace the whole stack um, um, with a Wasm Edge runtime. That requires us to build a lot of functionalities to Wasm Edge. So, for instance, you need to be able to connect to the database in a secure fashion. It needs to do that in a non-blocking, asynchronous way. So there's lots of underlying networking and infrastructure work that we have to do to make WebAssembly fit for this purpose. And then along the same line, we have expanded WebAssembly to do AI inference, which is perhaps one of our major use cases at the moment. People have PyTorch or TensorFlow models, but they don't want to use Python to do the model serving or the inference because it's too heavy. So you use WebAssembly for that. We are even expanding to say large language models like Llama, Alpaca. Those are languages that we are currently experimenting to see if we can use WebAssembly to do lightweight inference on them as well. So that would produce significant savings in the data center. But then again, I think WebAssembly as a whole is also evolving very fast. Perhaps the most important next step for WebAssembly is the component model, right? The component model really is um, it's try to componentize all the libraries and functions around WebAssembly so that they can be managed properly in its own repository tree, and be able to generate all the application interfaces from those libraries, right? So there's a lot of excitement that has been going on with server-side WebAssembly, and yeah, that's if you're interested, that's I'm we'd love to talk to you offline or come to our GitHub repository and see some of our latest talks. Yeah.
Yeah, thank you. And also, what's next now is the CNCF Sandbox project. Yeah, congratulations. Thank you. Thank
you.
Any questions from our guys? Oh, okay. Thank you, Michael. Thanks again. Okay, next up, Dr. Yulin Sun, and he'll give his presentation on Quark, high-performance app kernel sandbox. Welcome, Yulin.
Thank you for joining the meeting. Yeah, here I will introduce Quark. It is a high-performance application kernel sandbox. Here, I will first introduce what is Quark and why is Quark. Actually, Quark is just like another container runtime, just like Run C, and it provides OCI and CRI interface, but it just like Kata, it provides VM level isolation and security. It also integrated with Quasar so that Quasar can run Quark and Kata and other container runtime at the same place. Yeah, and it is developed from scratch with Rust, and it is open source project. Yeah, compared with Kata, actually it is both of them is a secure container runtime, but because Quark is developed from the scratch and with Rust, and it only designed as a user space as virtual machine OS kernel, so it is lightweight. It have low memory overhead and low startup latency, and it have high performance and high I/O throughput, and it's designed for the serverless scenario. For the serverless, because serverless they have limited user scenarios than the common container runtime, but and they have special requirement. For example, for the limited user scenario, it only needs support TCP/IP protocol stack, and it also need a quick start and quick startup and low startup latency. So when we developed the container runtime for the serverless environment, we can do some special optimization. Here later I can introduce how the Quark do the optimization for the serverless scenarios. Yeah. Actually, Quark's major goal is to provide a secure container runtime, and in the cloud industry, our secure isolation is mainly based on the virtual machine. And the Quark have the similar as virtual machine secure isolation, just like Linux virtual machine and the Kata. Here, we can see the architecture, compare the architecture between the Linux virtual machine and the Quark. The right side is the Linux virtual machine, and the Kata scenario, the Kata has designed like this. And the left side is the Quark, and both of them have 4 layers. First is the host kernel, next is the VMM, that's the virtual machine monitor. Then next is the guest kernel and the guest application. And both the Linux virtual machine and the Quark share same as the Linux host kernel, and they use KVM as hypervisor. And for the Linux virtual machine, this VMM is a QMO, and is all record from AWS. And over that is the Linux kernel. But for the Quark, actually we developed the VMM and the guest kernel together. Guest kernel we call it Quark QVisor, and the guest kernel we call the Q kernel. We design them together, and the Q kernel provide the system call interface, and this system call interface provide that compatible Linux system call interface, so that exiting this Linux container runtime, Linux container application can run over the Quark without change. Yeah, and the Linux actually Quark kernel is just like a Linux kernel. It provides a majority of OS kernel's features, and it's designed to only run in the Linux user space as a this user space application and work together with only the Quark visor. So that because VMM and the Gas kernel is designed together, so we can do some optimization and can do some special work other than the existing Linux Gas kernel. And the Quark is designed. At a Sandbox, and the Quasar is a Sandbox interface, and it's naturally we can integrate them together. In the Quasar, there's a container D will call the Quasar Sandboxer, and then there's a Quark task in this QVisor, and QVisor will enable the start multiple container in one Q kernel. With Quasar, we don't need to start the pause for Sandbox, pause container for Sandbox, so that we can save the memory. And also for the Quasar, it have one shim for multiple Sandbox, so we can save more memory and can get better performance, And actually, Quark is run as a virtual machine, just like Linux virtual machine. For the Linux, it's a common as x86 that's a virtual machine. And in order to improve performance, the major area we need to do optimization is from the I/O side. In order to do the optimization, that's Quark did some optimization for the I/O. Because Quark is running as a guest kernel, and the major guest and host communication channel is use the hypercore. That's the virtual machine's major communication channel, and hypercore's cost is very high, and because it needs to do the switch between the host and guest space, and all the that's x86 registers should be stored in the memory. And for this context, this registers context, it may include the float pound context. It takes about 1.5 kilobytes memory. It's the cost is very high. So Quark did some optimization to do this I/O. The first optimization is Q core. That is for the Q core, if Q kernel want to send some request to the QVisor, for example, read a file, and this request could be put in a shared memory queue. Q kernel put it to shared memory queue, and Q kernel's kernel thread will switch to another kernel task, and then another user space I/O thread will take over the request and process that. Because the communication is through the shared memory, so there's no context switch, so we can get better performance. Another is the U-Hard, that's based on the IOU-Run. IOU-Run is the Linux kernel's new feature. New IO infrastructure. It provides higher performance than the existing IO infrastructure. It's also a shared memory queue. They have a shared memory queue, the submit queue, and complete queue. Quark just create the shared memory, this IOU-Runs queue between the Q kernel and the host kernel, so that the request can pass through can bypass the QVisor, so we can get better performance. Another is RDMA. RDMA actually is a more advanced network protocol, and it can bypass the host kernel. Later can give more introduction about this, how to use the RDMA directly in the Quark container. This is some test result. We compare the Quark with other secure container, just like gvisor and Kata. Because Quark is created from the use Rust language, and it is developed from scratch, so it have less memory overhead. From here we can see Quark have about 10, 11, 12 megabytes overhead. gvisor have about 30, and Kata is very high. And also Quark have startup latency is very low. we can see this runc is the standard Linux container, and the Quark just a little higher than the runc, and it's better than evaluator, and kata is the most low. Yeah. And Quark's I/O throughput is also high. Here we compare it. We run that with NGX, with Redis and etcd. We can see Quark's performance is for the NGX, it is slower than runc, but better than other two. And for Redis, it's almost reached the runc's performance. For the etcd, it is also good. Yeah. Another thing is for the Quark actually. Quark actually is running as a runc as a standard Linux container. Its performance is actually its upbound performance limit is the Linux container. But actually, when we do the special optimization, we can get better performance than the runc than the Linux container. For example, for the network, one of them is use RDMA. RDMA is remote DMA. It has better performance than the TCP/IP protocol stack. But RDMA's interface is different than the TCP, so it cannot be used in the cloud native application. And also, it doesn't provide network virtualization, so we cannot use that for the in the Kubernetes. But Quark can do some optimization for that. First, because Quark can intercept the system call. For example, the socket system call, for example, system send and system receive. And when actually the TCP semantic is to send a buffer from a application to a remote. Actually, in this mode, the Quark can intercept this send and can get this send buffer and then use the remote RDMA, send it to the remote buffer, and then copy it to the server application. Based on that, we can say that Quark can bypass all the TCP/IP protocol stack, so they can get much better performance. Also, Quark also can, because it's a container runtime used in this container in the Kubernetes scenario, so that we can provide another CNI and container network interface to integrate with Kubernetes and to do the container virtualization work, to allocate the IP address, etc. This work, and it can work just like Flannel, just like other container runtime in the Kubernetes. When we enable this RDMA, if the cluster have RDMA, we can get better performance. Yeah, this is some test performance for this TCP socket over RDMA in the Quark. We can see this test is based on the Redis. We can see the up to 3 comparison is for latency, and the bottom is for the throughput. And for latency, this runc can compare with the runc plus host. As we know, that's in the container runtime, the container network's performance upbound is the host network. Actually, we can compare with this when we have this RDMA, TCP over RDMA, we can see this TSOR, the TCP socket over RDMA's performance latency is always less than the host network. The bottom is TSOR, it's latency, and for throughput, the top one is the TSOR, because its throughput is best. Yeah, and for the serverless scenario, serverless actually need the quick start and quick startup, and actually in the market, in this industry, the startup have only two startup mode. First is cold start, another is warm start. Cold start is start a new container, and warm start just keep the container container in the memory, and after they finish the first request, and when there's a new request, they just use the existing container, so it have higher memory footprint. And because Quark is a OS kernel running inside the user space, so we can do some interesting work, just like the Linux swap in swap out. But this for this feature, the guest applications user memory can be swapped out to a file, And when we start this, when we want to wake up this container, we just do the swap in for this application. Based on that, we can get a better better startup latency than the cold start. And because the memory is swapped out to the disk, so its memory consumption is less than the warm container. And based on that, we have a third startup mode. And this is the test result. And we can see this Quark container have the higher latency, lower latency than the warm start, and higher than the lower memory consumption than the warm start. Yeah. Okay. Yeah. This is my introduction about the Quark. Yeah. Quark now is integrated with Quasar, and Quasar can run different container at the same runtime, such like Kata and C and run C and the WAMP assembly. It is a good start to run that, to enable that in the cloud, so that different user scenario can use different runtime. Yeah.
Okay, thank you, Yulian. Okay, this is a really enlightenment presentation on Quark. Yeah, I think your capability for high performance computing is really fascinating. And I also have a question for you. Yeah. Could you share your future plan on Quark, both on technical plan and ecosystem plan? Yep, for your future plan.
Yeah, actually, Quark need to be the challenge of this this application kernel runtime is the compatibility with the Linux container. That's because Linux have about less than 300 system core. So far, Quark doesn't support all of them. In future, we will the most support for that and make it more compatible with Linux. This is the first work we need to work on. Another is for the use scenario. So far, the Quark is major used in the cloud, is designed for the cloud scenario. Actually, there is some other place we can use, but there's some place, some other area need a secure container. For example, in the software defined vehicle, that's in the car. For the vehicle OS system, we may use this Quark container. But in that scenarios, we need to develop a real-time that's a scheduler for this Quark container and other features. Yeah.
Yep. Thank you. So what about the other guys? Do you have any other questions?
Yeah. Hi. So you just mentioned that you use Rust as a development like a language for Quark. So at very beginning, right? So I just wonder why you choose Quark at very beginning, and can you share your experience on the Rust?
Okay. Yeah. Actually, Quark. Yeah, that's a good question. Actually, Quark is a OS kernel. It's an OS kernel. We need at that time, it's a requirement for its performance, because it's a system this OS level system development. Performance is critical. Another thing is a secure container, so we need a secure. And for the performance, we actually have very limited choice. That's C or C++ or the Rust. And C is the language that's developed the Linux, and C++ cannot be accepted by the Linux kernel. So C++ is removed, and the Rust is a new language just appear in recent several years, and it have more advanced feature than the C, and its performance just can reach a C level. Its advanced feature include the secure, that's a safe features like the non-pointer protection. All these features is critical for the security. So we choose the Rust, and I think it's after 4 years, I think it's the right decision at now. Yeah.
Okay, thank you. Thank you for sharing.
Yeah, thank you.
Okay, thank you, Yulian. So you move to the next one. Xiaobao Feng. who will be presenting on Quasar, an innovative multi-sandbox container runtime. Yep, Shama.
Okay, let's start. I will make introduction of the new open source project Quasar. It's an efficient multi-sandbox container runtime. As we said before, as the other two the other two said that we have integrated the Quark or WebAssembly or the micro VM sandboxer into this. So it's a multi-sandbox container runtime, and I will make introduction of it. So I will. First, I will give a history of talk about the history of the sandboxing container. Actually, in the early days, there's no such a thing as a sandbox in Docker. But Kubernetes has a notion of pod. They can run multiple containers in a pod. So they need such a thing as a sandbox. So in the early days, Kubernetes create a pod container and use this environment as a sandbox for running all the containers in the same pod. I think that's a compromised way, but it can make it work. And but in this way, that because Docker has to start a shim process for every container, so you will see many shim process running on the host of running the containers. It's of course a memory overhead, and it will affect this startup latency too. Here comes to the stage 2, the shimv2. Actually, the shimv2 is pushed from the Kata containers to the container D because in the early days, the Kata containers have many processes running on the host. It's even more than the containers running for run C, because they have so-called the Kata proxy or Kata shim, and every container has a Kata shim process. So there are almost more than 4 or 5 processes running on the host for one pod. So they want to reduce this, and then they made this shim v2. They upgrade the shim API and pushed it to container D. So for the shim v2, although the Kubernetes still creates a post container as a sandbox, but it will annotate it as a sandbox container, the so-called sandbox container. And in the shim process, it will determine if the created container is a sandbox container, and if it is a sandbox container, it will create a shim process. So it only create a shim process for one shim process for one sandbox. That reduces many processes. So we can see that for Kata, that you just need only one shim process for each pod, and they do all the things that of Kata proxy or the Kata shim before. And this is also brings the benefit for the run C containers too. They also just need to start one process, the shimv2 process for the run a Kubernetes pod. But in this way, the container and the sandbox management, the APIs are messed up in one set of the API. I mean, there's no such thing as a sandbox API. So especially in Kata, they just for example, the virtual machine management, or if the Kata want to do some resource hot plug, these actually are the management about the sandbox, but they are messed up in the task. So so here comes the third stage, that someone proposed the sandbox API to container D, and this is actually along with the background that more isolation technologies come into the container world. For example, we have the Kata containers, which is implemented in micro VM, and we have the wasm edge or wasm time with WebAssembly, and ABB kernel and unikernel and confidential computing. All these isolation technologies are connecting to the container world. So this makes Sandbox become more and more important. In this background, that the Sandbox API is proposed, and this makes the Sandbox the first class citizen in container. Then this makes first it removes the so-called post container. It makes the history, because Sandbox management is Sandbox management. They don't actually, if we have Sandbox APIs, they don't need this post container anymore. And the Sandbox management is no more mixed into the task API, because we have the Sandbox API. Although it split this Sandbox API and task API, but actually currently it is still actually the shim process is still the carrier of the Sandbox manipulation. So it's still this shim process to provide the Sandbox API, and because we need a shim process for every Sandbox or port. So it's still there is still a lot of shim process running on the host. Although we know that it is for doing the port lifecycle management, or do the restart recovery, but I think we can have some way to do it, and to reduce this shim process. So we want to make some better way to do this. And before we are doing this, doing the improvement, we want to make a clear definition of a Sandbox. So we are thinking what a Sandbox is, what an ideal Sandbox it is. So so this is our definition of a Sandbox. It's I think it's an environment, isolated environment to run containers in it. This definition, I think, is abstract. So we add some supplement. First, I think it can be a black box. So for the Sandbox, so it can be a black box for Canary or Israel, so that the Canary or Israel do not need to care about if there is a shim process, or what kind of files it need to start containers in it. They just don't need it. What they need to know that it's a black box, and it will expose the task API to it. So the container or Israel just call the task API through some address. In this way, that because it's abstract, so we can implement it in a highly integrated way. I mean, maybe we can just start one process. For example, for the virtual machine, we just need to start a QEMU process or hypervisor process as a Sandbox, and maybe one thread is enough for start a Sandbox. So it can be highly integrated. And the last one is that as a Sandbox is something running, so everything is running inside the Sandbox itself. So the Sandbox itself cannot manage the life cycle or resources itself, because all the things are running inside the Sandbox. They don't know the resources outside. So we need something else outside to do the management. That's actually what we want to make. This is called the Sandbox, and it will implement the Sandbox API, and it do the life cycle and the resource management for all the Sandboxes in one kind, running on host. So here comes the Quasar. That's what we already open sourced it, and provided different kinds of the sandboxers. First, we did some change of the Sandbox plugin in Canary and Israel, and to support calling the new Sandbox API that we changed. And we made a Rust Sandbox library for the common logic, and built the concrete sandboxes on it. We already implemented 3 kinds of sandboxes. It's a micro VM, Quark, and the WebAssembly, and all these sandboxes are implemented in highly integrated way. It just actually we have implemented that it's one process for each sandbox. So it's all implemented without the shim process, and the task API server are running inside this process. And then I will introduce individually of these three sandboxes. First one, the micro VM. It's actually we can compare it with the Kata containers. This architecture with the Kata containers. We can see that a sandbox is a virtual machine process running inside the namespace. It's just one process, and the task API server, which is for the container management, is running inside the virtual machine as a PID1 process, and it will. The Kennedy can call this task API through the virtual resource to the task API server inside the virtual machine. And as the virtual machine is running, all the processes running inside the virtual machine, so we need a sandbox process running outside on the host to do the management, as we said. This VM sandbox implemented the sandbox API and configured it as a proxy plugin into the Kennedy or Israeli. And when Kennedy want to do the sandbox management, they call the sandbox API to this process. And for the virtual machine, just what we do is to call the to start a virtual machine or to do the resource hot plug or unplug. And the IO are redirected out from a serial port or even a vSock to directly into the container D. That's also what we implemented. And then we get this app kernel sandbox. Actually, Yulin has made some introduction to it before, and this it's also a one process for Sandbox. It's a qvisor process, and it will run a qkernel inside this process. And this process will start a task API server inside it and serve the task API through a Unix domain socket, and container D can call it, call this call API through this socket, and it will start the containers inside the qkernel that inside this process. And for this, in this scenario, the Quark Sandbox, what Quark Sandbox do is it's not that that many as the micro VM sandbox, because you just need to launch this process and maybe do some bind mount of the folders or directories or some files. And as it's just a process, so the container IOs can be redirected out through the naming pipe. We just need to bind mount the name pipe to the namespace, and then qvisor or qkernel can recognize it. And the third one is the WASM web assembly sandbox. It is also mentioned before by Michael, and this maybe we can make it more lightweight, because for the WebAssembly, the startup latency is most important. So recently we implemented by forking a new process to as a WASM as runtime to run the container inside it. But actually, maybe if the WASM resolve the problem that they cannot redirect this SDDIO, maybe we can just start the WASM match runtime inside the process itself, and so all the things are running inside the process. That's actually a pattern of one of the pattern of the Run WASI project do. So because I think for the WebAssembly containers or WebAssembly apps, they the restart or the availability is not that important compared with this startup latency. So maybe we can make it one process to run all the containers. So these are the three sandboxes that Quasar provided, and we did some performance of the Quasar micro VM and compare it with the Kata containers. We can see that with this new architecture, the performance can improve very much. And we did two tests. First is the parallel startup time, and we can see that for the Quasar micro VM, all of the 50 ports start parallelly. The startup time can be less than 1 second, but for Kata containers, it's about 1.7 seconds. So we can say that it's a big improvement, and it also we can also see that it can reduce the memory overhead of about 1 GB for 50 ports running on a node. I think this is important for the IoT devices because or some memory restriction environment, because the memory is restricted. So we can say the 1 GB memory is also it's also a big save of the memory. And then I'd like to introduce some future works of what we want to about the Quasar. First, we want to make the Sandbox API specification. Maybe we can push it to the OCI community. I think we can make this Sandbox API standard of container. And then we have to say that the Quasar is in a preliminary stage, and we need to add more features into it. For example, we need to add some CLI tools, or we need to enhance the maintenance and the security. And also we need to add more support of technologies like Runtime and Firecracker, the VM, and or we need to support the running on the ARM architecture, and that's because if we want to make it on some edge computing scenario, we need to make it support on ARM. And the last one, I think it's also important that we need to support the confidential sandbox, because I think it's becoming much popular. And actually, I think in the future, maybe more customers would like to run their containers or run their applications in the public cloud in this way. So maybe it's also a very important thing that we have to do in the future. And this is our this is our website of project. So anyone is interested in this or want to add more the other features to it can submit the issue or PRs in this project. So that's all that I did, and any questions is welcome.
Okay. Thanks, Xiaobao, and it's fascinating to see your presentation on Quark. Any questions from other guys?
You mentioned confidential sandbox. How do you understand the confidential sandbox, and what application scenario do you think it is suitable for?
So first, I'd like to say what is a confidential, because so first, please allow me to introduce the confidential computing. I think actually in recent days, the confidential computing, there are many products released in the public cloud vendors for the confidential computing. For example, the micro VM, the Azure or the AWS also, or in the Ali Aliyun or release their computational computing products. And recently, it's said that its use case or its use scenarios is maybe it's financial or the healthcare or something, but like that. They have to make sure that all of their data and or codes are confidential and they cannot be released out. They cannot be picked when they are running. But actually, what I think is that right now, the virtual machine that we bought from the public cloud, it's like we said that it's like a house that without a curtain, so that everyone outside can see what is going on in the house. But for the confidential computing, for the if you in the future when you run your applications in the confidential containers, then it's like you put a curtain and set up this curtain, and then others cannot see what's going on inside this container. Yeah, that's what I think is confidential computing, and I think it will maybe it will become a default option of the application running on the public cloud in the future, maybe.
Okay, thank you for sharing.
Okay, and thank you, Saba. And next is Hao Zhong, and she'll presenting your topic on Isladi, a lightweight container runtime. Okay.
Hello everyone, I'm Tao Zhong, a contributor to Isladi. I'm honored to share Isladi with you all today. After listening to the three speakers, I think we all have a basic understanding of Sandbox technology and Quasar. Now I'm going to talk about Isladi, a lightweight container engine that's closely related to Sandbox technology and container runtime. Container engines are used to create and manage containers at the operating system level. They can bundle applications and their dependencies into a proto-container, allowing them to run in different environments. Container engines usually use Sandbox to isolate, process, and file systems within containers. So even if an application in a container is checked, it won't affect other containers or the host system. I will divide my sharing in 4 parts. Let's start with the first part. You might be thinking, why openEuler purpose with Isladi when Docker is so popular? Well, let's check out the CISDIC 2022 container usage report. As companies falling on board with containerization, the number and the size of containers being used in growing rapidly. The recent report showed that 5% of businesses are already using 5,000 or more containers. The number of containers per host has also increased by 24%, going from 14.6 to 15.7, and the maximum number of nodes has reached 2015. This can be a problem in environments where resources are limited or when deploying higher density container nodes, as the amount of resource containers consumed can be overwhelming. Additionally, container concurrency speed is one of the bottlenecks in large-scale deployment. This is why we are development a fast and light container engine, Isladi. Isladi got its name from the botnet ant in South America. Even though it's tiny, it packs a punch. Getting struck by one feels like getting shot with a bullet. It is one of the most powerful insects in the world. Isladi is the foundation of the Isladi system, offering adaptable, dependable, and safe support for all kinds of situations. It resumes small memory and has higher energy, just like its namesake. Let's learn more about Isladi. Isladi is a super lightweight container engine implemented by C and C++, is known for being fast, flexible, and is not limited by hardware specs or architecture. And ESRD supports the standard OCI interface and can easily integrate with other OCI runtime, like RunC, Kata, and Quasar, making it compatible with the container ecosystem. Due to its lower resource usage, ESRD is suitable for scenarios that require relatively higher resource restrictions on container energy usage, such as city, embedded, edge side, and so on. ESRD can run different types of containers, such as common containers, system containers, and security containers. Common containers are the usually ones that people use, like Linux containers. System containers are like common containers, but they can manage systemd service while running. They share the same kernel and the host machine, but only isolate some fields and proc, so they are not the same as a virtual machine. System containers are great for scenarios where you need to run source-intensive applications and move your business to the cloud. Secure containers are a mix of virtualization and container technology. They provide stronger isolation between containers by using a virtualization layers. So each secure container has its own kernel and lightweight virtual machine environment. This means the different security containers running on the same host machine won't affect each other. In the second part, let's take a look at the architecture of ESRD. On the diagram, you can see that ESRD has a command line interface that's similar to Docker, which you can use to manage containers. It also has a gRPC API that follows the container runtime interface standard. It implements the CLI gRPC service, which includes the runtime service and the image service. This gRPC service listens to the local unique socket, while kubelet runs as a gRPC client. As a demo, ESRD takes care of container lifecycle management, including image storage and transmission, container execution and monitoring, resource management, and networking. To make it easy to understand, we divided ESRD into 4 different modules and grouped them into 4 main service executors. You can see in the ground. The image service handles image management tasks like downloading, querying, and deleting images. The container service is responsible for container-related operations like creating, storing, and deleting. The network submodule takes care of managing the network of CLI ports. When a port starts, it is added to the network plan specified in the configuration file using CNI. When it stops, it is removed from the network plan, and the relevant network resources are cleaned up. Finally, volume service provides local volume management. The implementation of service relies on the 8 modules shown in the diagram. Ultimately running a process in container runtime. The container runtime implementation relies on system core, specifically the namespace and the C group features of Linux. Overall, the structure of ESRD is very clear, with each layer's function being well done. Next, let's analyze the difference between ESRD and Docker from the core chain. When Docker runs a container, it goes through a sequence of steps involving Docker, container shim, and then the container runtime. But ESRD starts the container through ESRD shim or LCL, and then through the container runtime. Also, to make Since easy for users, USID supports the conversion of Docker local storage and even allows for the porting of Docker containers to USID. In general, USID has a simpler and shorter call chain compared to Docker. This means that USID consumes less memory and has faster concurrent performance than Docker. In the third part, let's take a look at the performance comparison between USID and Docker. The first comparison is to start two identical RunC containers on the same machine using USID and Docker respectively. When we can see that the memory usage of Docker process is more than twice that of USID, and the memory usage of containerd is more than 6 times that of USID. The experiments clearly demonstrate that the USID consumes fewer resources compared to Docker, which can solve the problem of higher resource utilization of container infrastructure that we initially proposed. In addition to the memory advantage, let's take a look at the performance of USID and Docker in concurrent create, startup, stop, and the deletion of containers on the same machine. From the graph, we can clearly see that USID and RunC outperforms Docker and RunC in all 4 scenarios, and that USID and LCR is also outperforms USID and RunC in all 4 scenarios. The data provides that USID is far superior to Docker in concurrent performance, can break through the bottleneck of container concurrency speed. In the last part, we will use 2 simple demos to show how to use USID for container operation. The first demo demonstrates the command parameters provided by USID. This picture shows the main commands that instructions of openEuler, covering most of the commonly used application scenarios. These contain the operation interface of the container, such as create, start, stop, and delete. It also includes image-related operations such as download. Next, I will demonstrate how to use the openEuler command line. Wait a moment. Oh, you can see we can use pull command to pull the image we used to create container. In this demo, I pulled BusyBox and Ubuntu image. And if you want to create a container, you can use first you can use create command to create a BusyBox container, and you can see the state of container is created, and then you can start it. You can see the state become up, or you can directly use run command to run a container. Use this method, you can quickly see that the state become up. And if you want to pass the container process, you can use pass command. And if you want to restore it, you can use unpass the command to restore the container. And finally, you can use the stop command to stop the container, and set the time to 0 to short the time to stop container. also you can use rm command to delete the container. The second demo is to create a container in Kubernetes clutch deployed by Israel. You can see this is a YAML file. This is a container that run a date command in a loop, and we set the resource limiter. We limit the memory to 200 megabyte, and we can use apply command to create this this sandbox. We can see that pod state becomes running, and we also can see that the parts container and the application container in Isula. Next, let we use exec command to verify the resource limit we set in configuration. You can see that the value is the same as the configuration, and we also can use logs command to show the containers log. Finally, we can delete the container, use delete command. Through this demo, you can see Israel can be well integrated with Kubernetes. In short, Israel is an excellent container technology that outperforms Docker in memory consumption and can break through the bottleneck of container concurrency speed. It also provides rich commands and is suitable for various application scenarios. I hope today's sharing can help you better understand Israel. Thank you all.
Okay, thank you, Hao. Exciting to see that how study is shaping up to be a faster and more efficient container engine. Any questions from our guys?
So could you introduce your long-term plan for Israel?
Okay. Let me think. I think Israel's future development is divided into three aspects. The first, because RunC is still the most commonly used container runtime for enterprise. The first aspect is to migrate the default container runtime to RunC while ensuring the advantage of Israel. The second aspect is to continue to tracking the futures of upstream and downstream communities, providing more functions that user needs and refactoring and optimizing Israel. The third aspect is stable support for Quasar and the Sandbox API. For instance, the topic that SharePoint is sharing today is the combination of Israel and Quasar. Let's welcome SharePoint.
Okay, thank you. And SharePoint, it's your turn.
Okay. Can you see my screen? Yeah. Okay. Great. So thanks for all the presenters for spectacular presentations. So we're seeing different levels, different layers for the entire native cloud native stack. Like we seeing new technology, new sandbox technologies. Like yeah, so we have seen some new sandbox technologies like Runtime and Quark. What? You can see my screen? Can you see my screen?
Yes, but it's not full screen.
It's not full screen? How about this one? Oh, this is. Okay, how about now? Yeah. Can you see my screen now?
It's cool.
Yeah, sure, cool. Okay, thank you. So we think like new sandbox technologies and also a new type of runtime quizzer. And also we introduce ISRAD as a container engine. So we now know what are these levels are and how ISRAD and quizzer work separately. And it's time for us to review the entire cloud native stack again to get fully understand how these two components, ISRAD and quizzer, works together. So this is my contents today. So we're going to first give a brief introductions on ISRAD and quizzer project, and then give a deeper look into ISRAD's architecture for supporting Sandbox API, and then we will take a look at the performance and mention the roadmap briefly. So with Shabba's introductions on Quizzer, we can see that Quizzer is such a beauty with elegant architecture design and to remove the redundancy and improve the efficiencies. However, as a container runtime in the entire stack, Quizzer still needs driven by container engines like ISRAD. So my topic today is to focus on what kind of spark can be generated by combining ISRAD and Quizzer together. So look at this diagram. On the top level is Kubernetes. It is an orchestration and management application. So in Kubernetes, Pod Sandbox is the smallest scheduling unit. The container should always run inside a pod. However, there's no like sandbox semantics or concept in the container engine before sandbox API. So everything in the container engine before is container. So in other words, the container is the only first-class citizen in the container engine. So a pod or sandbox is always treated or scheduled as a container. So within Kubernetes context, it doesn't make a lot of sense because in Kubernetes, pod is always the smallest scheduling unit. So this is old architecture. So within this architecture, the pod config is always converted into a container config, and then using shim API to start pod, just like a container. So this is due to the lack of sandbox concept. So it makes it impossible for container engine to manage the sandbox directly. Also, the sandbox, the shim API introduced another shim layer, which will consume more memory resources and CPU resources. Also, will causing some maintenance issue due to another layer in the entire system. So as we can see in the Shabba's introduction, Sandbox is a solution and is a real magic to all the improvements like performance improvement and like maintenance improvement. So the design, this is new design. With the new design, we emphasize the Sandbox concept in container engine and container runtime. So in new design, we separate the sandbox management from container management entirely and utilize the Sandbox API to manage the lifecycle of Sandbox directly and use the text API to manage the container lifecycle. So that's decoupling the Sandbox management and container management, making the entire like a cloud native stack more reasonable and more logical. So let's look into more into detail of the older design and look at the problems we're having right now with all this with container engines with most container engines which using the shim v2 design. So they all using one API. So sandbox management and container management are all mixed into a Shim API. This because we lack of the sandbox semantics. That is the first problem we're having right now here. And also for each sandbox, we have for each sandbox we will have a Shim process for helping the management. So this is probably the redundancy of the Shim process because in the new architecture we probably just need one process that is enough. And also the Shim layer here making the call chain longer, which make it less robust for the entire system. As mentioned in the Chris' introduction, most of sandbox technology no longer need a Perth container. The existence of Perth container is a waste of resources, and also increase the attack surface, increase the risk of entire system. So with the new design here, I will put use micro VM sandboxer as an example. So we will Israeli will use Sandbox API to manage the sandbox directly due to we added a sandbox concept into Israeli and Quisa. We in these two components, they are aware of what is sandbox and how to manage sandbox. So we no longer mix the sandbox concept with containers concept again. So and also we only have one process here instead of using multiple Shim process for different sandbox. So it reduce redundancy of Shim process, save the memory and the CPU. And since we remove the Shim layer, Israeli can manage the container directly, without Shim layer. So also in the micro VM sandbox, we eliminate the redundancy of Perth container, which is not needed because in the VM in the virtualization we don't need a namespace or C group to help to restrict the resources. So this is the internal architecture for in Israeli and how we support Sandbox API. So in Israeli we have different layer like what introduced by Tao Zhong. And the first layer is called a CRI entry. It converts CRI request into internal Israeli request. The second layer is the executor. It receives requests from the CRI entry and do the configuration for the environment and also manage the data store. The third level is a service. It manages the lifecycle of sandbox and container. And the runtime is for managing, is for sending the request to Quisa. And the sandbox and the controller is for sending the sandbox API to Quisa to finalize the final management operations. So so with this design, we can clearly see that pod management has been totally separate from container management, which is decoupling the entire system by using different components. So yeah, so for the controller here, I'm gonna emphasize a bit because we are supposed to do backward capability. So previously we used Shim v2 for the other run times. So we implement two type of controller for the Shim controller. There's one called Shim controller, the one called proxy controller. For the Shim controller, we're gonna doing for the backwards capability for old runtimes like Kata or RunC. They are still using Shim layer. That means in Shim controller, we will still convert Sandbox to Sandbox object into a container object and reuse the shim v2 API again. And for the proxy controller, we're going to use the Sandbox API to manage the Sandbox directly, which is, I think, the best way for managing the container. So this is performance. We have seen similar performance in the Quisa's introduction. So with integration of Israeli and Quisa, boot time is reduced by about 50%, just due to two reasons. One is Israeli is very fast, and also we remove the shim process, which shorten the call chain. With all these two, we basically speed up our boot time. Secondly, is memory usage. This is very significant improvement. So the management components reduce the memory usage of the management components reduced by 99%, mainly due to the removal of the shim process. So especially in the large scale deployment, it's even more obvious that memory usage will be reduced. This is our roadmap. So for the first half years for 2023, this roadmap for Israeli Quisa project in openEuler. Well, in the first half year, we're gonna trying to cooperate with Quisa community to announce the Quisa to open source, and Israeli support the Sandbox API. In the second half year, we basically trying to enhance the functionalities, improve the reliabilities, and doing the proof of concept for commercial use. And finally, we're going to use a merge like Israeli Quisa features into openEuler 2309. So in the next year, we are trying to support consolidating our features into openEuler long-term support version, and doing some other type of sandbox support, like a app kernel, like a Quark support, and also enhance our features like lazy loading stuff. So yeah, I did a demo for Israeli Quisa. Let me share my another screen for better view. Wait a second. Yeah, can you see my screen now for the demo?
Yes.
Okay. Yeah. So first, we're gonna start the sandboxer, the Quisa sandboxer. We enable the log as a debug because I want to share more info when we running this sandboxer, and also we can listen to a sandbox a Unix socket, Unix domain socket. Quisa sandboxer can listen to this socket, and the DR option is basically specifying where we store the data. And let's take a look the Israeli config for Sandbox API support. So there's two things we need to notice, that in the Israeli config we added two fields, basically not two fields, one field, and also optimize one field. For this field, Sandboxer, we config Quisa Sandboxer using a couple of fields. The first one is address, which is the Unix socket address specified in the when we start a Sandboxer. And also we configure the controller as proxy. As I mentioned, we're gonna implement two type of controller, shim and the proxy. Proxy used for Sandbox API, and also definitely Sandbox API using the gRPC protocol. And also this field, this is for Sandbox API, and this is for text API. We convert CRI runtime into a Stream v2 version Sandbox task API, so that we can communicate with Quasar using this task API. So so let's start Isla-D as a container engine. So then we're going to start run a pod with this config, and we specifying runtime CI runtime with -r, and running with the pod.json config. And see here, we have created a pod successfully. It is in ready state. And we can also see that a Qemu being started, because I use Qemu as a hypervisor for this sandboxer. So next step, we're gonna create a container in the pod using using container.json config file. So I'm gonna copy the pod ID, specifying the pod ID and the config, container config and pod config. We can see the container is being created, and it is in created state. Next step, we're gonna start the container. So we can see that the state of the container is become running. So yeah, let's try to go over through the entire lifecycle management operations. Stop the container, and then remove the container. Yeah, it's gone. And let's check out the status of this port, and then we're gonna stop the port, and remove the port. So the port is gone as well. So this demo is quickly going through the entire life cycle management for Isla-D and Quasar. So this is all my my sharing today. So any question?
Okay. Thank you, Stefan. Is seamless integration of Isla-D and Quasar are truly impressive. Any questions from other guys? Okay, so maybe I have some interjects. As you mentioned, the task API at page 3. So what exactly does API task API look like? Is a new set of API like Sandbox API or something already exists? Yep.
Okay. Within my current implementation for the Quasar and Isla-D and Quasar, we basically reuse Stream v2 API. It's not exactly the same, but the modified version for the Stream v2. The difference is that when we normally when we start using the Stream v2 API to start a port, it will create a stream process. But in our case, as we think that we no longer start a stream process anymore. So there's where we modified. If we are going to if we use Sandbox API, we are not going to use we are not going to start the process again, stream process again, but reuse the text address exposed by Quisa, exposed by the Sandboxer. So it's kind of a bit different with Stream v2, but the logic behind it is basically the same. Any other question?
Oh, okay. Thank you. So that's all for today. If you don't have any other questions, then thank you to all the speakers for your sharing and your expertise with us. And thank you to everyone who attended the meetup. Holding from today's presentation can help you better understand this exciting field and its implications going forward. We look forward to seeing you again in our next events. Have a nice day. Okay, bye-bye.